So today what we're going to do is related rates again, and we're going to look at two types of relations. One relation is going to deal with volume, similar to like what we did yesterday with the sphere. And the other problem is going to deal with using a Pythagorean theorem. So we're going to use a Pythagorean theorem to get our relationship, okay? So those are the two focuses that foci. So those are the two things we're looking at today, okay? All right. So water runs into a conical tank. Okay, so conical, that means cone. All right. So we're looking at cone. All right. And at the rate of 9 cubic feet per minute. So this is a volume. Okay. And then the tank stands point down and has a height of 10 feet and a base radius of 5 feet. And what we're trying to figure out is how fast is the water level rising when the water is 6 feet deep. So let me give you a picture of this. Okay, so it's a cone, but the point of it is down. So you can draw like a circle like this. Okay, and right here, that would be the center of the circle. Okay, and then we would have a radius that goes to that center. So I'm going to draw it right across here. And then straight down is the point of this cone. It's like an ice cream cone, okay? You can think of it like that. And what we know is that this cone is its height is 10 feet. So that's from the tip to the center. Okay, and I'm going to draw it so it's outside. So it goes from here to right here. And we know that that is 10 feet. So I'm going to extend that just a little bit. So we know this is 10 feet. And the base radius, so this is the base, and the base of it is 5 feet. So we know this right here is 5 feet. All right, so what else do we know? Because we know some rates here, okay? So what we know, and let me get a thicker pen. So what we know is that the water is running in. So this is filling up. So I'm going to draw, this is a water level. Okay, so it's filling up with water and going up. And we know that dV dt. And how do I know that this one is going to be dV dt? Because cubic feet is volume, that's the dV part, and per minute, that's the dt part. So that's how I know that this is 9 and it's positive because it's running into the tank. So the water level is coming, or the volume in the tank is going up, it's increasing. So that'd be 9 cubic feet per minute. Okay, so how fast is the water level rising when the water is 6 feet deep? Okay, so we want to find, and we're going to label this H. Okay, so this is the water level right here. Now I'm going to extend this because the whole thing from here to here is this 10, but this little piece right here from here to here is changing, and that's H. So anything that's changing, we're going to put variables on because this height of the water, it's going up, 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 up. Okay. Also, there's radius of the water right here. So that's going to be R. Okay. And so we're going to need that. And so we're trying to find dH dt. But we're trying to find that when H is equal to 6 feet, because that's what this says. Okay, so we've taken care of everything. We've taken care of this, the conical, so that's how we know it's a cone. Tank stands point down. We also know that the rate at which the water is going in is 9 cubic feet per minute. Has a height of 10 feet. That's not changing. It's the height of the tank. A base radius of 5 feet. That's not changing because it's part of the tank. How fast is the water level rising when the water is 6 feet deep? Okay, so the relationship that we're going to use here, and this is a formula that I would actually give you on a test or quiz. So we need to know the volume of a cone, and the volume of a cone is V is equal to 1/3 pi r squared h. Now, what we have is a problem, okay? And our problem is this. We want to relate V and H only because we don't know anything about R. I mean, we know the base of the tank is 5 feet, but we don't know the base radius of the water, the top surface of the water level right here. Okay, so what we have to do is on a problem like this is we have to figure out a way to change R and make it become an H. And the way we're going to do that is through similar triangles. So what I have is a right triangle here, and I also have a right triangle right there. And so I'm going to draw in similar triangles. So that's part of what I'm trying to teach you today. Okay, so this is not changing. That's the 5 feet. All right. And I know this entire length from here to here is this 10 feet. And then we have this radius, and that's this radius right here of the water, of the top surface of the water, and that's R. And then this right here would be H, and that H would be from here to here. Okay, so we can set up a proportionate. So 5 is to R and we're going big to small. So this big side to the corresponding smaller side. So we're going to go the big side 10 to the small h, okay? So 10 is to h. So then we can cross multiply and we get 10r is equal to 5h. And we want to replace r. So what we want to do is solve this for r. So I'm going to divide both sides by 10. And I get r is equal to 5h over 10, which means r is equal to h over 2 because we can reduce that. So what this is telling us is that the radius is always going to be the height divided by 2. Okay, so we're going to put that back into this r right here. And now we're going to have a relationship that's only dealing with V and H, and then we'll take the derivative and we'll grab, by taking the derivative, we'll pick up a dv dt. We'll also pick up the dh dt that we're trying to find, and we'll be able to solve, and we'll have it all done, okay? So right here, I'm going to replace this r with h over 2. So now what I know is V is equal to 1/3 pi times h over 2 instead of r squared times h. Now I'm going to clean this up a little bit. Okay, so this would be 1/3 pi times, and this would be h squared over 4 times h. So that makes the volume equal to 1/12 pi times h cubed. Okay, so now it's just a matter of taking the derivative of this, and by taking the derivative of this left-hand side, I'm going to pick up dv dt, and over on this side, I'm going to pick up dh over dt. Now, you don't want to substitute any of these values in because they're changing, and because they're changing, right, that height of the water is not staying 6, it's going up, okay? And so you got to be careful. We have a tendency to just automatically put it in there, and we'll lose the dh dt by doing that, okay? So you don't want to substitute stuff in until after you've taken the derivative, okay? So d dt of v is equal to the derivative with respect to t of 1/12 pi h cubed. Okay, I'm going to slide this up a little bit. So that makes this side dv over dt is equal to, okay, so 1/12 pi is just a constant. So that's just 1/12 pi times, and then we take the derivative of h cubed, that would give us 3h squared times dh over dt. See how I pick up the dv over dt, and I also pick up the dh over dt. Now is where I can substitute everything in, or I can clean this up. So I'm actually gonna clean this up before I start substituting stuff in, because this becomes 3/12, which is really 1/4. So dv over dt is equal to 1/4 pi h squared times dh over dt. So now I can substitute everything in. So dv dt I know is from up here, it's 9. So this is going to be 9 is equal to 1/4 times pi times my height. So so the dh dt, okay, is going to be dependent on dv dt and also your h. That's why I had to give you the h here, okay, of 6 feet. So that'd be 6 squared, and then times dh over dt. So this gives you 36, and 1/4 of 36 would be 9. So this makes 9 is equal to 9 pi times dh over dt. And so I'm going to divide both sides by 9 pi. So I get 9 over 9 pi is equal to dh over dt. My 9's cancel, they make a big 1. So dh over dt, the simplified version of it, would be 1 over pi. Now, what are the units on this? Well, height is a length unit, and all of our lengths are being measured in feet. So this would be feet per, and then the time unit we're using is minute. Now, if we put that into a calculator, okay, and I've already done it, it turns out to be 0.318 feet per minute. So that means, okay, when the height of the water is 6 feet, the height is increasing 0.318 feet every minute, okay? So we want to write a statement with this. So the water level is rising, and I'm going to put the exact value. You could also put the approximate value. Either way is fine. 1 over pi feet per minute when the water level is 6 feet deep. Okay. All right. So the big idea here is volume. I would give you the volume of a cone or anything like that complicated. Okay. But you would have to come up with the similarity here that rewrites, that allows me to rewrite the equation so that it only involves V and H. That's what this was. That's what the purpose of the similar triangles here. It was to get us to be able to switch this to a formula that only deals with V and H, okay? So for this next problem, we have an airplane, which is right here, and it's flying at an altitude of 6 miles on a flight path that takes it directly over a radar tracking station. So right here's my radar tracking station, okay? And if the distance between the airplane and the radar tracking station is decreasing, so the distance between the airplane and the radar tracking station is this S. So we're labeling it S because it's changing, okay? And it's decreasing at a rate of 400 miles per hour when the distance between them is 10 miles. And then we want to know, what is the speed of the plane? So the speed of the plane is like, if you put this on the ground and you were going on the ground, what would be the speed of the plane? And that would be the derivative of this X right here. Okay. So let's start writing down the things that we know. So we know all right? Because the plane's coming in this way, as it gets closer, this distance is actually shrinking, okay? And we know that that distance between the radar tracking station and the plane is decreasing. So we know that ds over dt is equal to negative, because it's decreasing, and then 400 miles per hour. And that it is this only when s is equal to 10 miles. Okay. And then we want to know the speed of the plane. So the speed of the plane would be the dx over dt. So we want to find dx over dt. Now, what's the relationship? How can we relate x and s? Now, this 6 stays 6, so we can label it 6. It's flying at an altitude of 6 miles. That's not going to change. So the relationship we can use, because this forms a right triangle, is x squared plus 6 squared is going to equal s squared, or leg squared plus leg squared equals hypotenuse squared. So here's an example where we can use the Pythagorean theorem, because these distances are related because of the right triangle by the Pythagorean theorem. All right, so the relationship that we can use is x squared plus 6 squared is equal to s squared, or x squared plus 36 is equal to s squared. Okay, so let's talk. What happens when I take the derivative of this? Well, this left-hand side, I'm going to pick up, because there's an x over here, I'm going to pick up dx over dt. And over here on this right-hand side, I'm going to pick up the ds over dt. So I'm picking up the rate that I have, and I'm also picking up the rate that I am trying to find, okay? So we're going to take the derivative with respect to time of both sides of this relationship. So x squared plus 36. And we're going to take the derivative with respect to time of s squared. Okay, so the derivative of this would be 2x. So power down, so 2 times x, subtract 1 from power, take the derivative of the inside with respect to time, so that'd be times dx over dt. And then we're going to take the derivative with respect to time of a constant. Well, that's just going to be 0. So we're left with 2x times dx over dt equals, same type of thing is going to happen over here. It's going to be 2s ds over dt. And so we're trying to find dx over dt. So I'm going to divide both sides, or multiply by 1 over 2x. And so we wind up with dx over dt. And I realize I need to scoot my paper up just a little bit here. Dx over dt is equal to 2s over 2x times ds over dt. And here my 2's cancel. So my dx over dt can be determined by knowing the s, the distance between the radar tracking station and the airplane, the horizontal distance, and knowing the rate at which the s is changing, this distance between the radar tracking station and the airplane. So ds dt. So to figure this out, I actually need 3 things, right? I need the s, the x, and ds over dt. I have the s. I know this is 10. I know ds over dt. This is negative 400. I don't have x. But we have a relationship that deals with x and s. So by knowing this s, I can also use this relationship to figure out the x, okay? So when s equals 10, we know that x squared plus 36 has to equal 10 squared, and 10 squared is 100. So that'd be x squared plus 36 is equal to 100. And that would mean x squared would equal 64. And square rooting both sides, we get x is equal to 8. Now, really solving the equation, we get x is equals 8 and negative 8, but this is a distance, so it has to be positive, okay? If it turned out to be negative, then we could have that if it was over here on this side, okay? All right. So here we go. We can plug everything in. All right, so now we know, I'm going to slide it up a little bit more. Now we can find our dx over dt because it's equal to our s, which is 10, divided by our x, which is 8, times our ds over dt, which is negative 400. Okay, and so this becomes negative 4,000 over 8, which becomes negative 500 miles per hour. Now, it was asking for the speed, and speed is always positive, okay? So the speed of the airplane is 500 miles per hour, so we can write mph, when the distance between the plane and the radar station is 10 miles. Okay, and that's how you do this, okay? So one thing that happened in this problem that's unique is we did the Pythagorean theorem, right? Okay, and then we worked all our stuff out, right? But we needed to find something else. And what we had to do, right, because we got this dx over dt is equal to s over x times ds over dt. We had the s, we had the ds over dt, we didn't have the x. So we needed to figure out a way to get that x value right there. And we just went back to the relationship because the relationship we had dealt with x and s. Okay? All right, that's it.